So I suppose it's time to start. Now the problems we'll do today are probably not going to involve a lot of the numerical integration techniques, because to be honest with you, numerical integration, either you remember things about the trapezoid rule and Simpson's rule, or you don't. And it comes down to that. So just learn the trapezoid rule and Simpson's rule. Error approximation will give you the formulas if we ask you to do error approximation. So for that, you just have to know how to use it. So numerical integration is not a huge focus of our review. Should you feel the need to talk more about it, let me know. Improper integrals, we'll do some of that with the practice with the quiz. And we can talk about that on Wednesday. So these are more problems from earlier on. So the first one. Find the integral dx over x to the 5/2 minus x to the 1/2. Now we think about what things we've learned. So, like, is this a trig integral? Well, no, there's no trigonometry. Is this a trig substitution? No, not really. What are you looking for in trig substitution? Yeah, you usually look for square roots. And there's not a square root here. Okay. Is this partial fractions? Not yet. Now, it might be, because it kind of feels partial fraction-y, but why is it not a partial fractions problem yet? What's wrong? So it's not a partial fractions problem because partial fractions, you have to have a very particular type of function, namely a polynomial over a polynomial. The downstairs is not a polynomial. Now, the reason I say that is you look at the exponent. To be a polynomial, all your exponents have to be whole numbers. So if you have an exponent that's not a whole number, that's not a polynomial. So this is not a partial fractions problem yet. Well, a shadow of things to come. All right. Is this by parts? Not really. I mean, I can't see the two parts. Now, sometimes when we do parts, there's a hidden part when there's like a 1. But that's only useful if the derivative of what you currently have is nice. I don't think this has a nice derivative. So you're probably thinking, all right, so this is one we can't do. No. Just one we have to think about a little bit. So oftentimes when you have something that it's not obvious what to do, it means that there's probably either a way to rewrite it or a good substitution to make. And so be open to that idea. Is there a good substitution for me sitting somewhere that I can grab onto? So what can we do? Any ideas? Set u equal to square root of x. Now why might we think of that? Well, one reason we could think of that is really we can think of this x to the 5/2 as like x to the 1/2 to the 5th minus x to the 1/2. So that both of the terms I can think of as like a square root of x on the inside. So that's not a bad idea. So here, we'll try that. U equals square root of x. Now, before I solve for du, I'll note this is the same as saying u squared equals x. Because I can square both sides. All right, now I'll take the derivative of that expression. 2u du is dx. So that says the upstairs, the dx, becomes 2 times u times du. The downstairs, well, becomes u to the 5th minus u. All right. Now, what kind of problem do we have? Yeah, now it's really a partial fractions problem. It's a polynomial over a polynomial. Cool. Cool. So, we get to work. Well, let's see. Certainly the power upstairs is less than the power downstairs, so no need for long division here. Can we factor u to the 5th minus u? Okay, so you could pull out u, and then you get u to the 4th minus 1. All right. Can we go farther? Do we have to go farther? And the answer is, if you're doing partial fractions, how far do you have to get to? You have to get down to the point where everything is either a linear term, which means u plus something or u minus something, or a quadratic that doesn't factor. U squared plus something, u plus something. That means that's not fully factored. Okay, how can you factor u to the fourth minus 1? Aha, some people notice that u to the fourth is u squared squared. So u to the fourth minus 1 is like u squared squared minus 1 squared. So difference of squares. It's good. By the way, what happens to our u's? They cancel out. Ah, nice. Good. So we have 2, and then we have a plus b, a minus b. All right, now are we done factoring? No. Where can we go further? Yeah, the u squared minus 1. See that, that difference of squares? It's a fact so nice, we're using it twice. So, u squared plus 1, u plus 1, u minus 1. Now, can we go any further? No. No, that's as far as we go. At least as far as factoring, but we still have the whole integral to do. What we've done is we've done a substitution, which lets us rewrite it into a problem that we can recognize. Now we go and do some algebra on the side. So we have that 2, divide that by u squared plus 1 times u plus 1 times u minus 1 equals, I probably should have picked something with more space. All right, so there's going to be a u squared plus 1 term, a u plus 1 term, a u minus 1 term. What goes over the u squared plus 1? Yeah, so it's going to be a u plus b. So remember, if it's an irreducible quadratic, you have to have two pieces. Over the u plus 1, c, and u minus 1, d. So that means we've got to solve for a, b, c, and d. So we cleared both sides. We're going to end up with 2 equals a times u plus b times u plus 1 times u minus 1 plus c times u squared plus 1 times u minus 1 plus d times u squared plus 1 times u plus 1. Now at this point you have two options. Well, you have many options, but generally speaking you have two options. So one option is pick good values and get as many as you can. Oftentimes if you pick some really smart choices, you can get almost all or all of them. The other option is, if it doesn't look like that's going to help you much, is to expand and group coefficients. Let's see if the first option we can get anything. So what are some good choices we can make? 1, all right. So we'll choose u equal 1. So on the left hand we get 2. Over here the first term will go away, the second will go away, and the last one will become 4. Because we have 1 to plus 1, which is 2, and a 1 plus 1, which is 2. All right, so now we know that d should be a half. Any other good choices? Negative 1. So if you plug negative 1, left hand is still 2, the first term goes away, the last term goes away, the middle term is going to become 2 times minus 2. So that's negative 4c, so c is minus a half. Are there any other good choices? How about 0? Let's try 0. 0 is almost always a good choice to try. Okay, we try 0. We get 2. From the first part, what will we end up with? Negative b, because this a times u goes away. Negative b. From the second part, what will we end up with? Negative c. But what do we know about c? negative a half. So negative c will be plus a half. For the last part, what will we get? We'll get d, which is a half. So that's 1. So what can we do? Well, we get 2 equals negative b plus 1. We can solve for b. Do you see what it is? Negative 1. Because the half plus a half is 1. You move that across, you get 1 equals negative b, b equals negative 1. All right, are there any other good choices? No. But you know what? What don't we know? We only don't know one thing. And so that says just plug in anything you want. And then figure out what's true. So pick a number that's reasonable to work with. 2. Okay, 2 is reasonable to work with. Any number will work, but you don't want to hurt yourself. We love ourselves. We don't want to be mean. You know, we want to take care of ourselves. U equals 2. So 2 equals, and here, let's see what we have. We have 2 times a plus b. So that's going to be 2a minus 1. And then we have 2 plus 1, which is 3, and 2 minus 1, which is 1. So that's times 3. Plus, we'll have 1 half. Let's see, 4 plus 1, which is 5. And then we're going to have 2 minus 1, which is 1. And, whoop, why did I say plus a half? Minus a half, because c is negative a half. And then d is positive a half. So plus 1 half. Then here, we'll have it times 5. That's 4 plus 1. And then times 3. All right, interesting numbers we have here. All right, so let's see. We have the first, this end piece, that's 15 over 2. That's minus 5 over 2. If we put those together, what do you end up with? You end up with 10 over 2, which is 5. So now you can take that and move it across. And if you did that, you'd get that 2 minus 5, which is negative 3, equals 2a minus 1 times 3. Well, the 3's cancel. Negative 1 equals 2a minus 1. The negative 1's cancel. 0 equals 2a. So, what is a? 0. Good. Now we know. And knowing is half the battle. All right. The other half is doing. Okay. So now we got to do it. So, this will be equal to, okay, so we start here. We have a times u plus b. Well, 0 times u plus b. So that's a minus 1 over u squared plus 1. Then we have our c over u plus 1. And c is negative a half. So minus a half. That's 1 over u plus 1. And then we have d over u minus 1. And d is a half. So plus a half. 1 over u plus 1. And we go through term by term. The integral of minus 1 over u squared plus 1? Arctangent. So minus arctangent of u. Integral of negative a half times 1 over u plus 1? Now there's a negative a half. Natural log. U plus 1. Integral of a half times 1 over u plus, whoop. That's supposed to be a minus. There we go. That's a very thick minus sign. Plus a half. And the integral of that is the natural log of u minus 1. And then, because we want points, plus c. And yes, we do take points off for things like forgetting the plus c. But we also take points off if you forget to do things like write down in your du. We want good notation. There's a point set aside for notation. And so if you have bad notation, you're going to lose a point. So don't have bad notation. Have good notation. Are we done? No. Wonderful. I was worried we were done. Okay, what's left? Yeah, we've got to go back and substitute back in because we got to say, okay, this is really minus arctangent of square root of x minus a half log square root of x plus 1 plus a half log square root of x minus 1 plus c. And now we're done. There we go. Good. Good. A nice warm-up problem that only took us 20 minutes. All right. Next one. Find the integral of t squared over 1 plus t squared to the 3/2 power. What technique should we be thinking of? Trig substitution. What's sort of the clue about trig substitution? We see a square root, and there's some sort of addition or subtraction. Now, that being said, I'm going to go ahead and give you a warning. You see, we know what you know because we showed it to you. So that means that we know what you're looking for. So be careful. Don't just do a knee-jerk reaction. Be like, aha, it's this, so I'm going to go right into that. But see, now you know, but now you know that we know what you know. See? So now you're going to be cautious. Of course, that just means that we know that you now know that we know that you know. You know, it's a sort of back and forth game. So don't just run into everything. Be patient. Let the problem talk to you. Listen to it. Try to hear what it's saying to you. And oftentimes, it's trying to whisper things. In this case, we see a square root. It looks very clear. This should look like a trig substitution problem. All right. What kind of substitution? We've got secant, we've got sine, we've got tangent. Which one of those does this fall into? Yeah, this is a tangent one because it's the addition one where both things are being added together. All right. So, indeed, no big surprise. T should equal tangent theta. What does the derivative of tangent look like? Secant squared d theta. And for good measure, what is 1 plus, what is 1 plus t squared to the 1/2 power? So I'm taking the square root of tangent squared plus 1. It's secant. So we go through and replace all our parts. So the upstairs you have the t squared. That'll become tangent squared. The downstairs we have 1 plus t squared to the 3/2. Well, that's like 1 plus t squared to the 1/2, but cubed. So that says the downstairs is going to become secant cubed. And then we have the dt, which is secant squared theta d theta. So we've updated all our pieces. All right, well, we can see something. I mean, certainly we see that there's a bunch of secants, so we can cancel those off. So that's good. So let's see, what do we have? We have that this is the integral of tangent squared divided by secant. So now we ask ourselves, how do we integrate tangent squared divided by secant? Aha, somebody has spoken up and said, look, whenever you see a tangent squared or a secant squared, you should always have in the back of your mind. Well, first off, if you ever see a secant squared, you're like, I wonder if that's because we're making a substitution. But whenever you see tangent squared or secant squared, the other thing you should always have in the back of your mind is this nice little fact that tangent squared plus 1 equals secant squared, which really says, hey, I can hop back and forth between any even power of tangent and any even power of secant. So we could replace the tangent squared upstairs. It may help us, it may not, but we won't know unless we try. So secant squared minus 1 divided by secant. All right, what could you do there? Yeah, see, someone has suggested split apart the fractions. And we can do that because the minus is on the upstairs. We like it when the minus is upstairs. When it's downstairs, ugh. Upstairs, hey, good stuff. Secant squared over secant, also known as secant, minus 1 over secant, also known as cosine. Now, what is the integral of secant? Wow. Yes, natural log of secant plus tangent. Yes, good. Integral of cosine? Sine. I saw the sine. And it opened up my eyes. I saw the sine. Are we done? No, we're not. We got to go back to t. So how do you get back to t? You use a triangle. So we know that tangent theta is t because we have that tangent of theta equals t. That's sort of our clue. Well, t can also be thought of as t over 1. And the reason we want to write it that way is we like to think of the trigonometric functions as ratios. That's how we think of it in terms of triangles. So if it's not a ratio, we make it one. We draw a triangle here, put theta in a corner. It's the right triangle. It's not the wrong triangle, it's the right kind. Tangent is opposite over adjacent. What's our missing side? Square root of 1 plus t squared. Not a coincidence that that's what sort of got us going down this road to begin with. So, now we can do things. For example, we can talk about what is secant. Yeah, it's hypotenuse over adjacent. And someone else would probably say, hey, Steve, it's right there. Well, we're both correct. Square root of 1 plus t squared. Yeah, hypotenuse over adjacent. What's tangent? T, because we said it right there. But sine, ha 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 ha. Now we have to use this. Okay, sine is opposite over hypotenuse. T over the square root. I knew that triangle would come in handy at some point. And we're done. That one felt pretty good. I like that one. We should put one of those on the test. And guess what? There will be one of those on the test. Not this exact problem, but there will be a trig substitution on the test. How do I know? Because I saw the test. But the other thing is, there's only 6 topics, and there's 7 problems. So we said, look, nobody's going to be left behind. So everybody gets a chance. All right. Now let's do another nice, gentle problem. Find the integral of cosine theta log of secant theta plus tangent theta d theta. Your initial reaction to this is, I get to drop 4. No. That's not your initial reaction. Your initial reaction is, okay, I see trig. But this isn't a kind of trig where we use our trig identities. What's sort of different about this particular integral? The natural log. The natural log throws it out. So this is not really a trig integral, so there's something else going on. We have cosine theta. It's multiplying by log secant plus tangent. So we see a product. So we're thinking, ooh, it might be parts. But then we start thinking, where have we seen log of secant plus tangent before? It's not just random. It's the antiderivative of secant, which tells us that the derivative of log secant plus tangent is nice. So it's like, oh, I have 2 things multiplying together, and the derivative of the part that looks unpleasant is really nice. So that tells us we're going to go for parts. All right. And in particular, we can say, we want this part to be u. And this other part, well, that just has to be what's left. Oftentimes, if you see a log involved and it logs up in the top, it turns out to be an integration by parts problem. All right. Well, what can we do? Well, we take the derivative. And we've already talked about if we integrate secant, we get log secant plus tangent. So if we take the derivative of log secant plus tangent, we get back to secant. What's the integral of cosine? Sine. All right, so we're going to have u times v. So sine of theta log of secant theta plus tangent theta minus the integral of v du, which is sine theta secant theta d theta. All right. So at least the second integral feels more comfortable. We've gotten rid of that really unpleasant-looking natural log. How can we start to approach integration of sine times secant? Okay, secant is 1 over cosine, so if you have like sine times secant, it's the same thing as sine times 1 over cosine, or, fancy, sine over cosine. Oh, people are like, oh. So this is tangent. All right. Do we know how to integrate tangent? Did somebody say no? You can't say no. That's one of your 10. You got to know that one. Okay, so let's ask this again. Do we know how to integrate tangent? Yes. Yes, we do. What's the integral of tangent? Natural log of secant. And because we want points, plus c. There we go. So this was integration by parts. So I kind of like this one because when you first look at it, it sort of looks like one of these impossible, like, what can we do with this integral? But then we're like, yeah, okay. All right, we can do something. Let's see. All right. I can definitely feel like there's going to be a theme going on with a lot of these problems as we hop back and forth here. Let's try this one. Let's see. All right. Find the integral of t squared over t squared minus 1 to the 3/2. Now you're probably thinking, wait, Steve, we just did that one. But check it out. It's actually not the same. See, here it was a t squared plus 1. Now it's a t squared minus 1. And you're probably thinking, does that change anything? Yes. Yes, it does. Oh, what a difference a sign makes. All right. So what's our technique? Trig substitution. All right, not a big surprise. What substitution do we make? Secant. Yeah. So remember our basic rule is if it's a squared plus u squared, that's our tangent. If it's a squared minus u squared, that's our sine. And if it's u squared minus a squared, that's our secant. And in this case, so it's a variable squared minus number squared. So that's where we're at. So we're going to set u, or in our case, t equal secant theta. What's the derivative of secant? Secant tangent. All right, what is the square root of t squared minus 1? Tangent. Because we go back to that identity, secant squared equals tangent squared plus 1. All right, so let's see what this becomes. So with that substitution, what's the top? Secant squared. What's the bottom? Tangent cubed. Because what do we have here? We really have a t squared minus 1 to the 1/2, but then that's being cubed. So that becomes tangent cubed. And don't forget the dt term. That's why it's good to get into the habit of always writing down your dt's, so you don't forget them. And it's going to be really important next semester when you're doing multivariable calculus. Good times, good times. All right, so there's our integral. Well, we can do a little bit here. What can we do here? We can certainly knock out a single tangent. So there's a tangent squared. And, well, we can combine those secants together. So we get the integral of secant cubed theta over tangent squared theta, d theta. All right. Well, what can we do? Now, there's been a suggestion we could put in secant squared minus 1 for tangent squared. That is a possibility. However, I would offer a word of caution for doing that. The reason you want to be careful is if you're ever going to introduce plus or minus, introduce a plus or minus upstairs. When you put pluses or minuses downstairs, that's not fun. That's what we call not fun. Okay. So you want to avoid the not fun things. I'll be honest with you. If I saw this, I wouldn't be quite sure what to do right away. But when in doubt, there's always something you can try. And that's the following. If you don't know what to do, put everything in terms of sines and cosines, because oftentimes that can help you. I don't see a clear path out just yet. So I want to try to put everything in terms of sines and cosines. And maybe that'll help. I don't know if it will, but you can always try. Secant cubed, what does that become? Yeah, it's 1 over cosine cubed. And tangent squared is sine squared over cosine squared. So, let's see, what do we get here? All right, well, that would be, well, you flip it upside down, you get cosine squared. That's from this cosine squared, and you have a cosine cubed sine squared. All right, well, this may not have helped us much, but all right. You can certainly cancel off a bunch of cosines. So you get to the integral of 1 over cosine theta, sine squared theta, d theta. All right. Well, what can you do? This is definitely a challenging one. And I want you to know, we'll get an answer. We don't put the challenging ones on the exams. We put the fun ones on the exams. Any idea what we could do here? Now, there were other things we could try, and I can go back and say, here's some other things we could have tried. Ooh, partial fractions. We actually probably will end up going that way. Now, when you have cosines and sines, what is the ideal situation for you to be in? Like when you see a cosine sine, it's like, oh, I really want to be in this situation. Do you know what it is? Okay, I'll tell you what you don't want. You don't want to have an even power of cosine times an even power of sine, right? Because then you have to use power reduction. The situation you want to be in is to have either an odd power of cosine or an odd power of sine. Are we in that situation? Yes, we are. You see, cosine, right there, it's really to the -1 power. And -1 is odd. So, what could we do? Well, we can do the following. I can multiply top and bottom by cosine theta. And at this point, you're probably thinking, yes, I could have also multiplied it by 100. Why are you doing this, Steve? What's your motivation? Well, the real motivation is to say, I'm going to put that cosine theta d theta on the end. This is going to become my du. And you're probably wondering, what's your u? The u is going to be sine theta. Because that's what happens when you have when you have an odd power of one of the terms, you pull it out to the end. So, all right, now what? Well, the thing is, we can't have everything has to be in terms of sine. That cosine squared is no good to us. What do we do with that cosine squared? It's 1 minus sine squared times sine squared. And now we've got our substitution, and life is good. So this becomes the integral of 1 over 1 minus u squared times u squared du. Okay, now what kind of problem are we in? We're in partial fractions. All right, what's our next step? We got to keep factoring. Is this fully factored? No, not yet. It's going to be 1 over 1 minus u, 1 plus u, times u squared du. Okay, so now we're going to come do some work on the side. So, what do we have? We have 1 divided by 1 minus u times 1 plus u times u squared equals something over 1 minus u plus something over 1 plus u plus something over u squared. Oh, wait, well, that's not right. That's not right. What should it have been? C over just u and d over u squared. See, you have to have as many unknowns as the degree. This is a 4th degree downstairs. So whenever you have a repeated factor like u squared, you have to have like, okay, I have to have something over u squared. Clear your denominators. You're going to get 1 equals a times 1 plus u times u squared plus b times 1 minus u times u squared plus c times 1 plus u times 1 minus u times u plus d times 1 plus u times 1 minus u. All right. So there we go. Now, what do we do? So this is going to be equal to the integral of something over 1 minus u, something over 1 plus u, something over u, something over u squared. All right, how do we start? Okay, plug in 0. If you plug in 0, what do we end up with? That goes away, the a term. B term goes away. The c term goes away. The d term is going to be d times 1. So we get d equals 1, which tells us that d equals 1. All right, what else can we do? Plug in 1. If you plug in 1, the d term, the c term, the b term all go away. What happens to the a term? Become 2a. So we get that 2a equals 1. Oops, I should have said this is plug in u equals 1. And so we get that a equals 1/2. All right? What's next? Plug in -1. All right? What happens there? Well, anything with the 1 plus u goes away. This doesn't have a 1 plus u. So we're going to get 1 minus minus 1, which is 2, times minus 1 squared, which is 1. So we get 2b. No, it is 2b. But yes, I appreciate the joke. So b equals 1/2. What's left? C. All right. What can we do for help us figure out what C should be? You can plug in any number you want. You can expand out if you wanted to. If you're really, really patient, you could. Let's see. What's going to be the fastest thing? All right. I don't know. I feel like I keep always just plugging in things, and I just want you to know that there are other options. Suppose we were to look at the coefficients of u cubed. Let's just try this. The coefficients of u cubed. On the left-hand side, where we have the 1, what's the coefficient of u cubed there? 0, because there is no u cubed. On the right-hand side, come to the first term. What's our coefficient of u cubed? If you multiply it all out. Well, right, it'll be a, right? Because this is u cubed plus u squared times a. And a is a half. On our second term, what will we have? We'll have minus b, because there's minus u squared, that's minus u cubed times b, and b is a half. Yes? Yeah. So minus a half. On the c term, what will we have? We'll have u, a minus u, and a u. So that means we'll have a minus c. From the d term, what will we have? Won't have anything. Which means, what's true about c? C equals 0. So if you look at the coefficients, that's another way to figure out what's happening. So plus 0 over u. All right. So back to finishing up. So we integrate. What's the integral of 1/2 over 1 minus u? Is it 1/2 natural log of 1 minus u? It's negative, yeah. You gotta be careful. Oh my gosh, what a sneaky minus sign. That sneaky minus sign. If you miss it, you'll have a sign wrong. And of course, we could lose a point. And we don't want to lose a point. We want all the points. We worked really hard on this one. Here, you get 1/2 log of 1 plus u. Integral of 0 over u? 0. Yep. 1 over u squared minus 1 over u. Okay. Now, are we done? No. Because what is u? Well, we know, we go back, we said that u was sine theta. But wait a second, what is sine theta? Let's draw our triangle. So secant of theta is t over 1. So secant is hypotenuse over adjacent, which means that this missing side, that's the square root of t squared minus 1. Not a surprise, that's really what we should expect. So what is sine of theta? It is square root of t squared minus 1 opposite over hypotenuse. The square root of t squared minus 1 over t. So everywhere where I see a u, I can put that in. So we get minus 1/2 natural log of 1 minus square root of t squared minus 1 over t, plus 1/2 natural log of 1 plus square root of t squared minus 1 over t, minus 1 over u, t over square root of t squared minus 1 plus c. Aha! And this one probably took a little bit more work than the last one we did with trig substitution. Now, could we have gone a different route? Well, we can try. Suppose you don't want to embrace your secants and tangents. You don't want to embrace your cosines and sines. Let's come back here. Secant cubed over tangent squared. Now, I said don't introduce anything which has a plus or minus downstairs if you can avoid it at all costs. Well, what could we have done? Well, we could have done the following. We could have said secant cubed is secant squared times secant over tangent squared. And you're probably thinking, Steve, you're going backwards. Well, what's secant squared? Tangent squared plus 1 times secant theta over tangent squared. So that would become what? Well, you can break it up into parts. Tangent squared over tangent squared times secant, which is the integral of secant theta, plus secant theta over tangent squared. So you could have done that at the start. And so now you have the integral of secant over tangent squared. And at that point, it's not so clear what to do. So if you now do what we did before, let's see if that helps, if it's any simpler this time. 1 over cosine sine squared over cosine squared. If you do that, you'll see that what it simplifies to is cosine over sine squared. So this becomes the integral of secant theta plus cosine theta over sine squared theta. Now, do we know how to integrate secant theta? Yes. It's natural log secant plus tangent. Do we know how to integrate cosine over sine squared? Yes. How do you do that? You use substitution. U equals sine theta. Then we have du up on top. And what you end up with is the following. It's 1 over u squared. So it's actually going to be not plus, but minus 1 over sine. Now, it turns out, if you're very patient, you can show that these are equivalent. But you have to be very patient. So then there's a substitute back in. But looking at time, I think that's a good place for us to stop. All right. Okay, now that we have the warm-ups done, a couple more. And we'll just try to go at a little bit better pace right now. And I think we can get through these pretty quick. So we're starting to spot certain things. So there's a couple of hints on this one. First off, we really don't want that cubed root of x on the inside. So let's just go ahead at the start and get rid of that. And the way we get rid of that is by doing a substitution. So we're going to let u equal the cubed root of x. All right. In fact, you know what? I'm not going to call it u. I'm going to call it w. All right. I'm going to be a little bit wild and crazy. It's a wild and crazy guy. All right. So what do we have? Another way to write that is that w cubed equals x. Take the derivative of both sides, 3w squared dw equals dx. So this becomes integral of arctangent of u times the dx is 3w squared dw. All right, cool. Now we're more comfortable. All right, the inside of arctangent, nice and clean. The question is, what do we do here? Well, there's a huge hint. We have arctangent. Now, one way to handle arctangent, if there's like a 1 over 1 plus u squared, then it's easy substitution. But there's not. And so the other thing, of course, is to realize you copied it down, right? W. Okay. And so now you're like, look, there's no substitution. We don't know how to integrate arctangent, but beautiful derivative. Some of the most beautiful derivatives you might ever see. So if this part is easy to differentiate, and this part, yeah, we can integrate that, no problem. So that's suggesting by parts. Oftentimes, as with log, if you see arctangent, you should think integration by parts. So we're going to let this be our u, the part we differentiate, and this will be our dv, the part we integrate. And so we get that du is the derivative of arctangent 1 over 1 plus w squared dw. And the integral of 3w squared, well, that's not bad either. That's w cubed. So what do we get? We get uv. So we get w cubed arctangent of w minus the integral of v du. So that's w cubed over 1 plus w squared dw. Now, this integral, that's easier to work with. Now, this integral, it's a polynomial over polynomial, and therefore partial fractions. First thing we have to do is long division, because the power downstairs is less than power upstairs. So we're going to take, well, let's just do it here. 1 plus w squared divided into w cubed. Now we'll add in the extra terms, they're not there, so we put zeros. So, okay, w cubed, highest power is w squared. To get to w cubed, you multiply by w, which would give us a w and a w cubed, and you subtract, and lo and behold, we're left with minus w, and the game stops, because you can't multiply the highest power by something nice to get to minus w. So, that says that we get the following. We get the w cubed arctangent of w minus the integral of what we divided by our resultant, so that's w, plus our remainder, in this case it's a minus our remainder, over 1 plus w squared. Okay, so we're in pretty good shape. Why? Well, because we can do some of these parts. So for example, integral of w, well, that's not bad. That's a half w squared. And this integral is one you should be familiar with. We see it a lot. 1 plus w squared downstairs, w upstairs. If you were to take the derivative of what's downstairs, you'd get almost the upstairs. You're only off by a 2. So you can imagine if I put a 2 here and then a half in front. If I did that, what's the net effect? Well, the net effect is 1. But now I have a d something over something. That means it's a log. So we get a half natural log of 1 plus w squared. So when you see a derivative over a function, the integral of that's a log. Okay, let's be careful with the sign. This minus sign is going to go all the way through. So it's going to be a plus. And then, of course, because we want the points, plus c. And finally, we go back and say, what is w? Well, w is the cubed root of x. W cubed equals x. So we get x times the arctangent of the cubed root of x minus 1/2 times cubed root of x squared, which we could just write that as x to the power 2/3, plus 1/2 natural log of 1 plus x to the 2/3 plus c. And that's it. That's our answer. Good. Well, that one's not so bad. You just got to think. Substitution to make it easier to work with. Integration by parts. Life is good. All right, let's do another one. Definite integral. Well, that's good. That's definitely something we should know how to do. So, what's our approach? Well, x to the 5th log x squared. Well, log x, that's a clue. That's a hard thing to work with, at least if we're doing integration. Differentiation, pretty straightforward. So idea, we're going to let this be parts, and we'll let that be u, and that will be our dv. And the integral of x to the 5th, well, that's pretty straightforward. 1/6 x to the 6. The derivative of this is what? Well, 2 comes down, so we get 2 times natural log of x divided by x. And where does this divided by x come? It's the chain rule. The derivative of natural log is 1 over x, and there's a dx. So we're going to get uv. So 1/6 x to the 6 times the natural log of x squared. And because it's a definite integral, we're going to evaluate that from 1 to e. We'll take care of that in a moment. Minus integral v du. So let's see what we're going to do. We're going to have a 6 times a 2. That's a 1/3. We have x to the 6 and a 1 over x. So that's x to the 5th. And we have a natural log of x. And we have a dx. Now, these look similar, but you'll see that here the natural log of x was squared. Here it's not. So that's good. Don't forget this is a definite integral, so we update our bounds. All right, so before we do our next piece, now if you look at this also looks good by integration by parts, and it should work better because we've simplified it. It's a simpler expression. Over here, if you plug in 1, log of 1 is 0. Plug in e, log of e is 1. It's nice. So what do we end up with? Well, this is going to evaluate to 1/6 e to the 6. Okay, now we continue on here. So, similar process. Once you commit to something, stay committed. U dv. What's the antiderivative? Well, it'd be 1 over 18 x to the 6. What's du? 1 over x dx. So, we get, this is equal to 1/6 e to the 6 from there, minus, and here I'm going to be careful because there's a minus, so I'm going to use a point-saving technique called parenthesis. You can think of it as parenthesisalis or something fancy. Like, ooh, a fancy technique. All right, uv. uv. So 1 over 18 x to the 6 natural log of x. And this is evaluated 1 to e. Minus integral of v du. Now here there's a 1 over 18. X to the 6 and 1 over x would be x to the 5th dx. Okay, so remember this minus is going to come through to both terms. So let's take a look here. Before we distribute the minus here, what would happen? Well, similar to before, if you plug in the 1, natural log of 1 is 0. Plug in e, natural log of e is 1. And therefore, what you'll end up with is 1 over 18 e to the 6, and you're going to subtract that. Here, you can integrate this. Well, the integral of x to the 5th is x to the 6. 6 times 18? Yeah, right. It's 108. You just put a 0 in. Well, no, it's a little bit more than that. All right. X to the 6. And whoops, don't forget, it's a definite integral. So we evaluate that from 1 to e. So let's see where we're at. We have our 1 over 6 e to the 6 minus 1 over 18 e to the 6. Minus makes this a plus. Now you have to evaluate this. So plus 1 over 108 e to the 6 and minus 1 over 108. Now if you wanted to make this look pretty, you could say, I want a common denominator of something. Well, what's common? 108 is common. Why? Well, turns out 108, 1 over 108 is 1 over 108. To get from 18 to 108, you multiply by 6. So this is minus 6 over 108. And here, to get from 6 to 108, you multiply by 18. So this is 18 over 108. And factor out the e to the 6. 18 plus 1 is 19, minus 6 is 13. And 13 and 108 have nothing in common. So it's 13 over 108, e to the 6 minus 1 over 108. And that's our answer. Now be a little bit careful here. There's something that a lot of people might be tempted to do at the start, which is they might be tempted to say, hey, isn't it the case that the natural log of x squared, isn't that equal to 2 natural log of x? And the answer is no. What is true is that the natural log of x squared equals to natural log of x. So this is a yes. See, there's a little subtle difference. Here, the squaring is happening inside the log function. Here, the squaring is outside the log function. So pay attention. Be careful. Do not fall for easy mistakes. If you're going to make mistakes, make them beautiful, glorious, crazy, and interesting. Not easy mistakes. All right, another one. Find the integral of 1 over the 4th root of 4y squared plus 8y plus 3. Now, we see this and we say, aha, I see a square root, and I see there's adding and subtracting going on the inside of the square root. So that's probably a suggestion. We are heading towards something involving trig substitution. So if we were going in that way, we want to say, all right, I want to write this in one of our forms. U squared plus a squared, u squared minus a squared, or something else. Now we've got to be really careful here, because you might be like, okay, complete the square. And if you weren't being careful, you say, okay, take the middle term 8, divide by 2, 4, so we should add 16. But that's wrong. You see that 4? That messes you up. So you want to be really careful. So here's how we be careful. And being careful, it does take a little bit of time, but not much time. In fact, the amount of time it takes to be careful is so small, and the amount of points you save are so many, it's just a good thing to do. So if what's in front of your variable y squared is not a 1, factor it out. So I'm going to have 4, and I say, okay, the next thing is I have y squared and 2y, and now I pause. And I say to myself, what do I need to add? Well, what I need to add is what would make y squared plus 2y plus a square? So I want this to be a square. So the answer is add 1. Because lo and behold, if you check, it'll be this quantity is y plus 1 squared. Now, because our leading coefficient is 1, we're okay with what we were doing before. So that's our square. But let's be careful. This will give us a net of plus 4. We want plus 3, which means we're off by 1. In fact, we need to subtract 1. So we say, okay, so what we really have is the following integral. 1 over the square root of 4 times y plus 1 squared minus 1. All right, now we're ready to go. And let's see. Well, let's go one more step further. I could combine this 4 inside of here if I wanted to. And you know what? I want to. I want to do that. So I can think of this as 2 times y plus 1 squared minus 1 squared. There we go. So this is our u, and this is our a. Now what's the right kind of substitution? It's u squared minus a squared, which means the right kind of substitution for us to be making is to let u equal a secant theta. Or, in our case, 2 times y plus 1 is equal to secant theta. Take derivatives. 2 dy equals secant theta tangent theta d theta. All right. So, we don't have a 2 up there. That's all right. We can do something like this. 2, and then put in a half. The other thing we could do is move the 2 over. The same effect. The same effect. On a side note, what we have is that the square root of 2 times y plus 1, all that squared minus 1 squared, well, that becomes the square root of secant squared minus 1, which becomes the square root of tangent squared, which becomes tangent. So, we get that this is equal to the 1/2 integral. The downstairs becomes tangent, and the upstairs becomes secant theta tangent theta d theta. The tangents work out nicely, almost as if it was designed to work out nicely. So, what do we have? We have 1/2 integral of secant. That's something we should know. Log of secant plus tangent. Now, if we wanted to, we could draw a triangle, or we could be smart and say, you know, I know what things are. Here's my secant. Here's my tangent. So I can just use that information. So we get 1/2 natural log. Secant would be 2 times y plus 1. And tangent, well, it's this square root. In fact, it's this square root right here, if you multiply it out, plus the square root 4y squared plus 8y plus 3 plus c. And there's our answer. Done. Easy. See, once you get warmed up, they tend to go a little faster. Unless, of course, you make a mistake. So be careful. Be really careful. Just sort of think about things. And good. Now, could you have drawn a triangle? Absolutely. Absolutely. And if that makes you comfortable, definitely do it. You should do what makes you feel comfortable. After all, this is your test too, and you should get to have the full experience. All right, final one, cool down problem. All right, so what's our cool down going to be? Integrate 0 to 2, 2x cubed minus 14x over x squared minus 2x minus 3. So this lets us really test our partial fraction skills. Polynomial over polynomial. First step, we check our degrees. 2 is less than 3, so we need to do a long division. So we're going to take x squared minus 2x minus 3, divide that into 2x cubed. There's nothing, x squared, minus 14x, and nothing. I have x squared. To get 2x cubed, I need 2x. So multiply 2x by everything. 2x cubed, multiply 2x by minus 2x will give us minus 4x squared. And 2x times minus 3 gives us minus 6x. And we subtract that, and we get 4x squared minus 14 minus minus 6, so that's minus 14 plus 6. That's minus 8x and 0. So I have x squared. What do I need to multiply to get 4x squared? Well, the answer is I need to multiply by 4. So I'm going to have plus 4. So I'm going to put 4x squared minus 8x minus 12. Subtract. Those cancel. Those cancel. Coincidence, but hey, we love coincidences. And 12. That's our remainder. So, long division gets us to the following. This equals the integral from 0 to 2 of the 2x plus 4. And then our remainder, 12, divide that by x squared minus 2x minus 3. All right. Now we need to tackle this. So the next part is we need to factor it. If it can factor, and does it factor? Probably. Almost everything we'll give you will factor. And if it doesn't, we've either made a mistake or something interesting is happening. We love interesting things, but more likely there was a mistake made by somebody. So how does it factor? Well, I need two numbers that multiply to negative 3, add to negative 2. Well, if I put in, let's see, minus 3 and plus 1, that does it, right? Because negative 3 times 1 is negative 3, and you have a minus 3x and a plus x, which is minus 2x. All right, good. Now we're ready to do our partial fractions computation. So off to the side we go. So what do we have? We have 12 divided by x minus 3 times x plus 1 equals, now the important thing is to remember the form. So a over x minus 3, b over x plus 1. Clear your denominators. 12 equals a times x plus 1 plus b times x minus 3. And now, well, solve for a and b. I like to choose. Choose x equals negative 1. What happens? Well, you'll get 12 on the left-hand side, and over here, that term cancels. Minus 1 minus 3 is minus 4, so you get minus 4 times b. So that tells us that b is negative 3. How about x equals positive 3, right? That's a good choice. I almost wanted to say positive 1, but no, 3. Well, we get 12 equals a times 4, that's 4a, and then the second term drops out, so we get a equals 3. All right, so that tells us what a and b are. So we update what we're trying to integrate. Integrate 0 to 2 of 2x plus 4 plus a, which is 3 over x minus 3, and then b, which is negative 3, so minus 3 over x plus 1. All right, good, dx. So this is actually a big parenthesis there. Now we just have nice pieces. See, we do partial fractions to get nice pieces, each piece of which we can integrate. So we integrate bit by bit, x squared, and 4x, and 3 natural log of x minus 3. Now, here I'm going to do something I normally don't do. Normally I don't worry about absolute value, but I can see I'm going to need to evaluate. And if I were to plug in 0, I'd get a negative. So this is a time when I'm actually going to pay attention and put an absolute value. Technically, they should always be there. But in practice, we just put them when we need it. And if it's not working out, throw them in. All right. Here, do I need absolute value? Well, not between 0 and 2. But you know what? I'll do it just so that this other one doesn't feel so awkward. You know, it's weird to go to the party and only see, you know, your log without an absolute value and look across the room and there's a log with an absolute value. I mean, what do you say to each other after that? It's just, how do you recover? It's hard. It's hard. Okay, plug in 2. So what do we get? We get 4 plus 8. And here we'll get 3 natural log of 0 minus 3. So that's 3 natural log 3. Then we're going to get minus 3 natural log of 2 plus 1. Wait, hold on. Wait, I'm plugging in 2. I plugged in 0. Plug in 2. 2 minus 3 is negative 1. Absolute value. Log of 1 is 0. Then here, you get minus 3 natural log 3. There we go. That's when you plug in 2. Subtract, plug in 0. You're going to get 0, 0. And here, 3 natural log 3, because absolute value of negative 3 is 3, minus 3 natural log of 1. So that goes away. So we end up with 12 minus 6, because there's minus 3, natural log of 3. And that's the answer. A good answer. Life is good. Okay, well, lots of practice. I think we're just about done. A little bit more practice, and we'll be ready to move on to a new topic. Well, that's next week. But for now, that's it. Bye.